Hello everyone, this is Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equation. So let's get going. Problem solve. D cube minus 3d minus 2 into y equals to x square. Firstly, let's find order and degree of the given differential equation. Identify the highest derivative. Here d cube is the highest derivative, so order will be 3. And the highest power of the highest derivative is a degree. Degree is 1. Or just write the given differential equation as d cube y minus 3dy minus 2y equals to x square. We know that d is a differential operator, right? Then d square is d square by dx square and d cube is d cube by dx cube. Now we can write our equation as d cube y by dx cube minus 3 into dy by dx minus 2y equals to x square. Here d cube y by dx cube is the highest derivative, so our order will be 3. And highest power of the highest derivative is a degree. Degree is 1. Right? Now coming to the problem. Given differential equation, d cube minus 3d minus 2 into y equals to x square, which is in operator form. F of d into y equals to q, where f of d equals to d cube minus 3d minus 2 and q equals to x square. Now we need to find the general solution to the given equation, just given by y equals to yc plus yp. Here yc is a complementary function, yp is a particular integral. We'll find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by taking RHS or putting RHS 0, we'll get f of d into y equals to 0, which is a homogeneous equation of the given non-homogeneous equation. And we'll find yp using 1 by f of d into q. So let's begin with yc. Using the auxiliary equation, we are going to find complementary function. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d cube minus 3d minus 2. Let's replace differential operator by m, so that we'll get f of m equals to m cube minus 3m minus 2. Then our auxiliary equation becomes m cube minus 3m minus 2 equals to 0. Now let's find roots using synthetic division method. Roots of this equation using synthetic division method. Now place the quotients of m's. Quotient of m power 0 minus 2. Quotient of m power 1 minus 3. Quotient of m square is 0. Quotient of m cube is 1. Right? Just consider the polynomial m cube minus 3m minus 2 and see which satisfies this polynomial. Now let's check for 1. M equals to 1. 1 cube minus 3 into 1 minus 2 is 1 minus 3 minus 2, which is 1 minus 5 minus 4, which is non-zero. Right? Since m equals to 1 does not satisfy the polynomial, let's go for minus 1. Is equals to minus 1, minus into minus plus 3, minus 2, which is equals to minus 1 minus 2 is minus 3 plus 3, which is equals to 0. So m equals to minus 1 satisfies this polynomial, right? 1 plus 0, 1. Minus 1 into 1 is minus 1. 0 minus 1 is minus 1. Minus 1 into minus 1 is 1. Minus 3 plus 1 is minus 2. Minus 1 into minus 2 is 2. Minus 2 plus 2 is 0. Again, this gives another polynomial. M square minus m minus 2. So here you can factorize it. Just write minus m as minus 2m plus m minus 2. Now take m common from the first two terms, you'll get m times m minus 2. And last two terms remains the same. Here m minus 2 is common in both the terms, so let's take m minus 2 common. We'll get m minus 2 into m plus 1, right? So from m equals to minus 1, we'll get m plus 1 equals to 0. And we can write m cube minus 3m minus 2 as product of m plus 1 into m minus 2 into m plus 1. Okay? Or see which m satisfies this polynomial. Try for 1. We'll get 1 minus 1 minus 2, which is equals to 1 minus 3 equals to minus 2, non-zero. So m equals to 1 does not satisfy this polynomial. So let's try for m equals to minus 1. We'll get minus 1 whole square minus of minus 1 minus 2, which is equals to 1 minus into minus plus 1 minus 2, which is 2 minus 2, 0. So m equals to minus 1 satisfies this polynomial, right? 1 plus 0, 1. 1 into 1, 1. Minus 1 plus 1, 0. 1 into 0. 1 second. See, we have to check for 1 equals to minus 1. Okay, sorry. 1 equals to minus 1. Then we'll get minus 1 into 1. Minus 1 minus 1. Minus 1 is minus 2. Minus 1 into minus 2 is plus 2. Minus 2 plus 2 is 0. Again, this gives a polynomial m minus 2. It's clear that for m equals to 2, it satisfies. M equals to 2 satisfies this polynomial. 2 minus 2 is 0. Right? If you put 1, you'll get 1 minus 2, which is minus 1. If you put minus 1, you'll get minus 1 minus 2, which is minus 3. Right? So m equals to 2 satisfies the next polynomial. 1 plus 0, 1. 2 ones are 2. Minus 2 plus 2 is 0. Right? So from m equals to minus 1, you will get m plus 1 equals to 0. And from m equals to 2, you will get m minus 2 equals to 0. Now we can write the polynomial as product of m plus 1 into m plus 1, m plus 1 into m plus 1 into m minus 2, right? So our auxiliary equation becomes m plus 1 into m plus 1 into m minus 2 equals to 0. The product of these three should give this polynomial, right? Product of these three must result to this. Let's check it. M plus 1 into m plus 1 is m plus 1 whole square. Expand this using a plus b whole square formula. M square plus 1 plus 2m into m minus 2, which is equals to m square into m is m cube plus 1 into m plus 2m into m is 2m square minus m square into 2 is 2m square plus into minus minus 2 into 1 2 plus into minus minus 2m into 2m is, sorry, 2m into 2 is minus 4m is equals to, here plus 2m square minus 2m square gets cancelled. We'll get m cube plus m minus 4m is minus 3m minus 2. See, we got the same polynomial. So we have done the verification. Right. Now equate each factor to 0. M plus 1 equals to 0. M plus 1 equals to 0. M minus 2 equals to 0. From M plus 1 equals to 0, I'll get M equals to minus 1. And from M minus 2 equals to 0, we'll get M equals to 2. M equals to minus 1, 2 are the roots of our auxiliary equation. Here minus 1 is repeating twice, so we can call the first two roots as equal roots and 2 as distinct root. Therefore, M equals to minus 1, 2 are the roots of f of m equals to 0, which are equal and distinct. What I mean is, two equal roots, equal and real also, okay, these are real roots. Two equal roots and one distinct root. We know that when two roots are equal, m1 equals to m2, then our complementary function will be c1 plus c2x into e power that equal root into x. If we have a distinct root, then our complementary function will be another constant into e power the distinct root into x. Now let's write the complementary function to our problem. Yc equals to, firstly let's write for equal root minus 1, since we are having two equal roots, so we'll get two terms under brackets, c1 plus c2x into e power equal root into x, plus now we are going to write for the distinct root 2, another constant into e power distinct root into x. Then yc equals to c1 plus c2x into e power minus 1 into x is minus x plus c3 e power 2x. So we got yc here. Now let's find yp, particular integral. Particular integral you can find yp using 1 by f of d into q, which is equals to f of d. We have d cube minus 3d minus 2 and q is x squared. So this is of 1 by f of d into x for n, or 1 by f of d into x for k form, right? Since we are having n equals to 2, so we'll get derivatives of q till d square, and from here we'll get all higher derivatives of q 0, right? Just nothing but d power k of x square is 0 for k equals to 3, 4, 5 and so on, right? We'll show you in detail. Let's find derivatives of x square. Derivative of x square is 2x and d square of x square is derivative of 2x, right? We can write d square of x square as derivative of x square. This is equals to, we have the derivative of x square value, which is 2x. This is equals to 2 into derivative of x. This is equals to 2 into derivative of x is 1, which is 2. Now find d cube of x square, which is equals to derivative of d square of x square. This is equals to derivative of d square of x square value is 2. And we know that derivative of a constant is 0. So we'll get d cube of x square is 0. Likewise, we'll get d power 4 of x square is 0. D power 5 of x square is 0. And so on. In general, d power k of x square is 0 for k equals to 3, 4, 5 and so on. Right? Now coming to yp. We notice the denominator is in descending order form, right? And we need to take the lowest degree term common from all the terms, or write the denominator in ascending form and then take the lowest degree term common from all the terms. Okay, let's take minus 2 common from all the terms of denominator. Since the two terms does not have any minus 2, so what we'll do is we'll just multiply and divide minus 2 to these two terms. Okay, plus I'll write minus 2 as plus of minus 2 for my convenience. Now what we can do is just take minus 2 common, then we'll get minus 2 into d cube minus 3d by minus 2 plus 1 into x square, right, which is equals to 1 by minus 2 into 1 plus d cube minus 3d by minus 2 into x square is equals to minus 1 by 2. I'm writing 1 by, I can split this as 1 by minus 2 into 1 by 1 plus, see here, we can write d cube minus 3d by minus 2 as some minus of d cube minus 3d by 2. Right? Then in the next step, we can write 1 by minus 2 as minus 1 by 2 into 1 by 1 plus into minus minus d cube minus 3d by 2 into x square. Right? So this is of the fraction is of 1 by 1 minus x form. So in the next step, we can write it as 1 minus x whole inverse, and then we can use binomial series expansion to expand 1 minus d cube minus 3d by 2 whole inverse, right? Or let's see in ascending form. This is equals to 1 by minus 2 minus 3d plus d cube into x square. Now we need to take minus 2 common from all the terms, right? Since the last two terms don't have minus 2, so what we'll do is we'll just multiply and divide minus 2 to the last two terms, right? Now it will be easy to take minus 2 common. So now take minus 2 common from the two terms. We'll get minus 2 into 1 plus minus 3d plus d cube by minus 2. Okay, I'll show you clearly. 1 by minus 2 into 1 plus minus 3d plus d cube by this minus 2 into x square, right? Now we can split this as 1 by minus 2 into 1 by 1 plus, we can write the numerator as d cube minus 3d by minus 2, right? Into x square, which is equals to, now write 1 by minus 2 as minus 1 by 2 into 1 by 1. We can write this fraction as minus of d cube minus 3d by 2 into x square, which is equals to minus 1 by 2 into 1 by 1 plus into minus minus d cube minus 3d by 2 into x square. See, you'll get the same thing, right? So now we are going to write 1 by 1 minus x into 1 minus x whole inverse form. This becomes minus 1 by 2 into 1 minus d cube minus 3d by 2 whole inverse into x square. So this is a 1 minus x whole inverse form. Now we need to use 1 minus x whole inverse expansion, 1 plus x square plus x cube plus so on. See why we are writing this to 1 minus d cube minus 3d by 2 is, again here also what we can do, we can just multiply these two terms with minus. Okay, then we'll get 1 plus x form. We'll get the total fraction as 1 by 1 plus x form, right? Then we need to use 1 plus x whole inverse expansion. We know that 1 plus x whole inverse is 1 minus x plus x square minus x cube plus so on. The signs will be changing alternatively. Okay, so without making confusion, we'll just prefer 1 minus x whole inverse. Okay, if there is a possibility to write yp in 1 minus x whole inverse, right? Here we got the possibility, so we wrote in 1 minus x form, 1 minus x whole inverse form. Fine. Let's expand 1 minus x whole inverse. Keeping in mind that we'll get only values till d square. Okay, values till d square, d and d square, and d cube of x square, d power 4 of x square, all higher derivatives from d cube is 0. So we can expand this as 1 plus x d cube minus 3d by 2 plus x square plus cube and so on. See here we'll get d cube minus 3d by 2. We know that d cube of x square is 0. Okay. And here we'll get d cube minus 3d whole square by 2 square, which is equals to 1 plus d cube minus 3d by 2 plus expand d cube minus 3d whole square. D cube whole square plus 3d whole square minus 2 into 3d into d cube by 2 square is 4. Right? If you notice, we are having d cube whole square, which is d power 6, and here we'll get d power 4, and here we'll get 2 3 is 6. D into d cube is d power 4. Right? Here we'll get 9 d power 4. So finally we are going to get d power 4, d power 4, so d power 6, d power 4, d power 4, which are, here you will get d square, right? Not d power 4, sorry. 9d square. D square, okay, we are having the value of d square of x square, but also here we are having d power 6 and d power 4, which are higher derivatives, which has to be neglected because d power k of x square is 0 for k equals to 3, 4, 5, 6 and so on, right? And also the next term, from next term, we'll get exactly higher derivatives, d cube whole cube plus or minus 3d whole cube, okay? We'll get higher derivatives. If you want, you can check for d cube minus 3d whole cube, which is equals to d cube whole cube minus 3d whole cube minus 3 into d cube into 3d into d cube minus 3d. Okay, so here you'll get d power 9 minus 3 d cube, okay, 9d, not 9, 27 d cube minus, here d cube into d is d power 4, d power 4 into d power cube is d power 7 higher derivative, right? Again, d cube into d is d power 4, d power 4 into d is d power 5. So you are getting higher derivatives in this term also, right? We don't get any d or d square term here. So you can neglect all the terms from x cube, right? From here you can neglect all the higher derivatives. So we have to neglect higher derivatives from d cube, d power 4, d power 5 and so on, right? Now coming to yp, yp becomes minus 1 by 2 into 1 plus d cube minus 3d by 2 plus d cube minus 3d by 2 whole square. And we know that the terms from x cube, x power 4 becomes 0, right? I mean the derivatives, higher derivatives of x square from d cube, d power 4, d power 5 is 0. So we'll neglect terms from here. This is equals to minus 1 by 2 into 1 plus d cube minus 3d by 2 plus d cube minus 3d whole square by 2 square into x square. Why we are taking only the first two terms? Because d and d square exist only in the first three terms. From the next terms we will get higher derivatives, exactly higher derivatives. Is equals to minus 1 by 2 into 1 plus 1 by 2 into d cube minus 3d plus 1 by 4 into d cube minus 3d whole square. Expansion is d cube whole square plus 3d whole square minus 2 into d cube into 3d into x square. This becomes d cube whole square is d power 3 into 2, which is d power 6, and 3d whole square is 9d square. And third term, 2d cube into 3d is 2 3s are 6 into d cube into d. D cube into d can be written as d power 3 plus 1, so that you'll get 6d power 4, right? Now this equation becomes 1 plus 1 by 2 into d cube minus 3d plus 1 by 4 into d power 6 plus replace second term by 9d square minus replace third term by 6d power 4 is equals to, here we can neglect higher derivatives d cube, d power 4 and d power 6. Since d cube of x square is 0, d power 4 of x square is 0 and so on. D power k of x square is 0 for k equals to 3, 4 and so on, right? So neglect higher derivatives from d cube, d power 4 and so on. We are going to neglect d cube, d power 6 and d power 4. Then yp becomes minus 1 by 2 into 1 plus 1 by 2 into minus 3d plus 1 by 6 into 9d square into x square. This is equals to minus 1 by 2 into 1 plus into minus minus 3 by 2 into d plus 9 by 4 d square into x square. Then yp becomes 1 into x square. Minus 1 by 2 into 1 into x square is x square minus 3 by 2 into derivative of x square plus 9 by 4 into d square of x square, which is equals to minus 1 by 2 into x square minus 3 by 2. We have the value of derivative of x square, which is 2x plus 9 by 4 into d square of x square is 2. 2 ones are 2 2s are 2 2 gets cancelled. This is equals to minus 1 by 2 into x square minus 3x plus 9 by 2, which is our required yp. Now let's write the general solution. The general solution is given by y equals to yc plus yp. Already we have yc c1 plus c2x into e power minus x plus c3 e power 2x, and we have yp minus 1 by 2 into x square minus 3x plus 9 by 2, which is a required solution. We have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.